Eh, So at the end of the presentation, we are going to share with you the slides and also the video of this new training session. This training session is expected to more or less 1 hour, as always. So we're going to start with in this case, with my presentation talking about the Ecoforect Academy and Ecoforest. So the Ecoforest Academy, as we are doing now, is basically online training course, but now that the situation with the pandemic is improving, our idea is to start again with the face-to-face training courses. With the online training courses, we are going to do regularly, 2 per month, as we were doing in the past, and we are going to try to bring new topics to these online trainings. We would like also to invite some expertise, like today is the case of Hugh, to join us and to talk about specific topics of this industry, not just about Ecoforest and our heat pumps, also some other technologies that is related with heat pumps. And for the face-to-face training courses, we have been working with our partners all over the world to create what is the Ecoforest Academy training centers. Nowadays, we have 12 places available in different countries like Spain, UK, the Netherlands, Ireland, Australia, Belgium, Portugal, Italy, and Germany. So if you want to be in person and if you want to touch our units and you want to know more about us, also we can organize, we are going to organize regularly trainings in these places. So in our website will be also the option to book trainings there. So that's are more or less the places available. Usually have one heat pump working, a training area, and also places to also show you some presentations. So today we are going to start with this training, with this presentation about us. So Ecoforest is a heat pump manufacturer located in Spain. If you don't know us, basically we are doing air source and ground source heat pumps. We are a very young company. We started in this business in 2014, so 7 years of life more or less, and we are growing a lot in the last years, thanks to our exclusive solutions in this heat pump business. At Ecoforest, we offer complete support from the designing and prescription of a project, also during the commissioning and installation, and also in the after-sales service. Our product range of heat pumps is like this. We have 3 ranges. What we call the Ecogeo Basic and Ecogeo HP is water-to-water heat pumps. It's divided in these 2 ranges because in this case is what we call domestic range, and this is the high power range. In the domestic range, we have these powers, 1 to 6 kilowatts, 1 to 9, 3 to 12, and 522. All these heat pumps are inverter technology, so they modulate from this power below up to the power on the right. And we have the option to cascade these units up to 3 units, and available in single and 3 phases. In the case of the 1 to 6 is with natural refrigerant inside with Air 290. When you check this surname as Pro, is because we are using Air 290 or propane as refrigerant. With this unit, we can provide domestic water heating, active cooling, and passive cooling. The only difference between this range and this one is question of the elements included. In the question of the basic and compact, we include all the elements of the installation inside, like expansion vessels from brine and production, the circulation pumps. But in high power, that is a unit for mainly commercial and industry. In these cases, the circulation pumps or the expansion vessel is installed outside of the unit. We have 3 powers, 1240, 1570, and 25100 kilowatts. The service possibles are the same: domestic water heating, active cooling, and passive cooling. And these units are more or less similar. in question of software, configuration, control strategies, and the technology is basically the same, a water-to-water heat pump. We have trainings done speaking about this range. So if you want, we can share with you all the details. And we have been also doing trainings regarding these EcoAir units. The EcoAir is a monoblock system, a air-to-water heat pump. We have 4 powers, the 127, the 129, the 3212, and the 420. In this case, they are mainly with air 219 as a natural refrigerant inside, and we only have one exception, that is the 420 kilowatts. In this case, is with air 410A as a refrigerant. The service provides our domestic water heating and active cooling. And the installation possibilities, it depends a lot on the indoor module. In the EcoAir, we are offering one external module and hydraulic connection to an internal module. For the internal module, we have 7 possibilities. Today, we are going to talk about open loop, so we are going to talk more about the water-to-water heat pumps. Then will be Hugh explaining you how these systems work and what solutions you can have with these units also. So at Ecoforest, we are working especially in 3 ways. We try to differentiate ourselves in the technology. For that reason, we are doing a lot of research and a lot of R&D. We have reinvesting in the company a lot of money in looking for new solutions, looking for doing more flexibility to this heat pump business. On that way, we are also trying to combine the heat pumps with other technologies, like it could be PV, thanks to our EcoSmart range, or also in the brine system, that is the topic today, to combine different collection systems, like open loop with air source, or boreholes with air source. So we have been working in giving to our partners solutions, also to the designers. And the 3-way or the open door that we are working now is with the refrigerants. As you know, the restrictions with the traditional refrigerants are increasing a lot recently. So we are looking for new solutions regarding the refrigerants, and our bet is for the 290, not only for the air source heat pumps, we are also doing units with the H219 for the water-to-water. If you need to install indoor, the restrictions are higher to use H219 due to the inflammability of this refrigerant, but we are working on solutions that we will release soon also on the water-to-water heat pumps. So with our units, we are working in the single house or in the domestic sector. We are also working in commercial and industry. So we have plenty of reference done in multi-dwelling installations, in hoteling offices, in hospitals, or in industries like agriculture or business areas. So for each of the cases, we can provide a solution. For that reason, you will have a team, and a specific team dedicated for you. In my case, I'm working on sales department, but I am also providing a technical backup in the designing of a project, or also with these training courses. So today we are going to speak about open loop. For that reason, I invite Hugh to join us because he has more experience than me, and he's an expertise on this topic. So I'm going to give him the turn to speak about what he's doing at Agua Enodo. So if you want, Hugh, you can start now with your presentation. Thanks so much for being with us today. It's a real pleasure, and so it's your time.
Thank you. Thank you. Now let's get the share screen on the right screen. I have more experience than you, Adrian. I've also got many more years than you. So that's where I would say that's where my experience, my experience lies. But no, thank you very much for the invite today. I'm very pleased to have the opportunity to speak to some of your current and prospective clients for Ecoforest. So as Adrian said, my speciality is open loop ground source heat pump systems. I've been permitting or working on these since about 2003. I sit just up the road from Ecoforest in Vigo. I'm in Pontevedra in Galicia, and I work on projects from Galicia, mostly in London, Australia. I see we've got Richard on the line. Hi, Richard, and New Zealand. But obviously the market for open loop ground source heat pump systems is, just like closed loop, is growing. So I'm going to hope to just give you a bit of my take on an open loop sort of a project flow, something that you might go through if you were looking at an open loop ground source heat pump system. So let's see if I can move this forward. There we are. So this is just a quick overview of what I'll be talking about, some of the differences between open loop and closed loop. And then, as I said, I'll run through a typical open loop ground source heat pump project summary. So just to make sure that we're all on the same page, and this will be perfectly familiar to most of you, but obviously open loop requires some source of water which we take to the heat pump, and then we reject that water. In the case of many systems, that would be via wells, via boreholes to and from an aquifer. And of course, the closed loop, we're talking about some sort of circulated fluid within a pipe in the ground, typically horizontal, vertical, whatever that might be. So open loop, there are a number of different types of open loop. We've obviously got the conventional dedicated abstraction borehole, dedicated injection borehole, where we take water out of an aquifer, pass that water past the plate heat exchanger, and then put that back into the source aquifer. Depending on the loads, we have different flow rates, and if you need more flow with a bigger load, then you have more boreholes. So may have single borehole systems or multiple borehole systems. Something that's very, very popular in the Netherlands and increasingly popular, I think, elsewhere. We've got a reversible system where instead of having a dedicated abstraction well and an injection borehole, we actually have a dedicated warm well and a cold well. So these are for sites that may have a fairly balanced heating and cooling load at the surface. We would take water out of a cold well when there's a cooling load at the surface, warm up that water and dump that into the warm well, and obviously reverse the system when there is a heating load at the surface. So we've got cold water, we can dump that in the cold well. So both boreholes have the capability to abstract and both have the capability to accept injected water. The idea behind this, even though it's a slightly more complicated, expensive setup, is of course that we try and take advantage of creating a warmer and cold bubble around those dedicated warmer and colder wells. With the system at the top there, which is you might call a pump and dump or unidirectional system, we actually want that flow of warmer or colder water to move away from the abstraction borehole, so that we're not pulling warmer or colder water back. But with a reversible system, we're actually hoping to take advantage of that and try and get some extra efficiency out of the system. And there are others. Obviously, we can have taking water in and out of surface water, a lake or a river. We can have wells near rivers, and we've got a couple of systems in Scotland at the moment where we're taking water out of a borehole near a river. There's a hotel on the bank of a nice river. We then dump that water back onto surface water, and you probably heard recently that it's very popular at the moment to be looking at utilizing mine water. Essentially, an open loop would be any source of water within the environment. But what we're going to focus on today would be the borehole options. Open versus closed loop. Just a few sort of the very highlight points of open loop versus closed loop. Obviously, these are sort of rule of thumb opinions, but open loop tends to have intrinsically a higher risk to the project than closed loop. The main reason for this is because we can't know what an abstraction borehole and injection borehole will achieve in terms of its sustainable yield before we've actually drilled it. Now, I'll go into this in a bit later in some more detail, but we may have an excellent driller, we may have an excellent design of borehole, but we may fail to achieve the flow of water that we want from that well in a given location. With the best will in the world, we just don't know what goes on in the ground. Now, closed loop, I would argue in this respect is lower risk because we're installing a loop in the ground. It has it has known thermal properties. We know what the circulation rate in the loop is going to be. We can design that better. We can design out the risk. So this is all at the design stage. We try and manage the risk of open loop by going through the feasibility study process, but I think probably the moral of the story here is to ask a professional hydrogeologist, someone that's familiar with the area, familiar with the aquifer. Of course, I guess bound up in that risk as well is the presence of an aquifer beneath your site. Obviously, with open loop, we can only operate an open loop if there is an aquifer beneath your site. With a closed loop, we've got much more freedom. We don't need an aquifer. We can drill into any rock, install loop into any rock. Open loop has much more environmental requirements on it. And leading on from that would be the licensing requirements for an open loop. As I said, I work regularly in a number of jurisdictions around the world, notably the US and the UK. Very similar in Australia and New Zealand as well. The licensing requirements. When you're taking water out of the environment, it will nearly always incur interest from the local regulator. And because we're abstracting and injecting, we're typically required to have an abstraction license and a discharge permit. Now, those come in many different names, but basically, we need an approval to take water out of the ground and put it back in the ground. That can have significant requirements on things like an environmental impact assessment, how we drill and how we test those abstraction and injection boreholes, the rigor to which we have to assess the sustainability and the environmental impact of an abstraction and injection is obviously compared to a closed loop system, which again, in most jurisdictions that I've worked in, certainly there are few actual regulatory requirements that we have to go through. Sometimes we have to notify the regulator, sometimes we have to submit some plans, but generally we don't have to get these two sets of approvals because we're drilling, putting loop in the ground, and then basically typically backfilling those boreholes. So the closed loop tends to be designed and installed under sets of standards, guidelines, or best practices, depending on which country you're in. And I'd argue that's a lower level of regulation than actually applying specifically for your scheme. And again, that moves on to the next bullet point, the longer project schedule. We often need to apply to drill the borehole before we've even tested it and started applying for the actual license. So before you get the rig on site, you have to have a permit to drill. Often that takes time. It takes some level of design as well, because obviously we need to tell the regulator how many boreholes we want, where we want them, and how much flow we're expecting to take from them. Whereas with a closed loop system, you can design the closed loop system, you can get a rig on site without any approvals necessary. So whilst the drilling schedule might actually be similar, the project schedule's definitely drawn out by the regulatory requirements. Maintenance, with an open loop system, we're obviously interacting with the environment in a closer way. We're abstracting raw groundwater out of the ground, so this isn't treated groundwater, raw groundwater out of the ground, and we're dealing with that at the surface in our plant. There are heat pumps that, with certain water quality parameters, they can go through the heat pump, but often we'll have a plate heat exchanger that separates the plant and the heat exchanger, the heat pump from the ground. And when we're dealing with raw water directly from the environment, when we're changing its temperature, potentially changing the pressure as we pump it, this can have dissolution and precipitation reactions happening with that raw water, and therefore there tends to be maintenance required on the plate heat exchangers, on the submersible pump that would be in the borehole, All these things dealing with the environment obviously has a higher implication for maintenance. Whereas with a closed loop system, of course, we select our circulated fluid. We have a pump that's isolated. The pipes isolate us somewhat from the environment. And if we've chosen our pipe right, if we've chosen the fluid in the pipe right, then we should have a lower maintenance on closed loop. The footprint of the installation, well, of course, this would depend on the size of the loads and the balance of the loads, but generally we could say that an open loop system would have a smaller overall footprint. In this regard, I'm not talking about single domestic, I'm really talking about sort of the larger commercial systems. That's because once we've installed the abstraction and the injection well, we can put that in a basement, we can put that in a trafficable manhole cover, it can be subsurface, essentially has a very small footprint. Obviously, then we have the pipe run to and from the plant room, but the footprint can be very small. And because the flow rates from a single borehole can be quite high, we've got some systems that operate at 50 liters a second. Obviously, the thermal capacity of a single borehole or a borehole pair can be a lot higher for the same rate that you would get from a closed loop field. So with the closed loop field, again, obviously this can be buried, but it does have a larger footprint. We don't necessarily sanitize the land that's on, but certainly we have to have regard for where the closed loop field sits, and we have to think about the sort of development or landscaping that goes on above that. So as I've said, these items are generally true for commercial size sort of ground heat exchangers. And one point I hadn't included here, but I wanted to point out, someone says, which are most efficient, open or closed loop? You probably expect the answer to be, well, it depends. It depends on the ground conditions. It depends on the groundwater conditions. It depends on the size of the thermal loads, and it depends on the balance of the thermal loads. So anyone looking at let's say a heating only system, once we're looking at closed loop, we obviously have to have fairly careful regard on what the ground temperatures are going to be. Whereas with an open loop, we might get an opportunity, depending on the ambient groundwater temperature, to start abstracting, to continue abstracting an ambient groundwater temperature, stable temperature, and we have a better opportunity to have a smaller, more efficient system. Whereas if we have a very well balanced system, then obviously closed loop, we have an opportunity to make that a smaller, more efficient system as well. So the most efficient, it depends. So as I've said, this might be a typical sort of open loop schematic. You can see that we've got the abstraction borehole on the left, the injection borehole on the right, and the schematic here is supposed to demonstrate that these can be happily installed into the basement of a building. We don't necessarily need space for that. We don't necessarily need any footprint for that outside of the building, although we do often put them in the pavement outside buildings in urban settings. And you can see that in this case, this is a pump and dump system. So we have the abstraction well on the left-hand side. This draws water to the well so that you can see we have something called a cone of depression around that well, and the blue lines sort of dovetailing down to that well is supposed to indicate the fact that we drop the water level in one well in order to take that water out. Then you can see the sort of the plate heat exchanger somewhere in the basement that isolates the heat pump from the water in that from the heat pump. And then we have the injection well on the right hand side of the two wells there. When we put water into the ground, we obviously raise the water level in that borehole as water is forced into the rock beneath your site. And we have to obviously have some fair regard to those, and I get onto this more later, into the hydraulic interference that we would get from those wells. So how do we have regard for this hydraulic and thermal interference? I would recommend on any open loop project, as well as closed loop, that we have a staged approach to that project. And the first stage on that should be a feasibility study, hopefully by which time we have, at the very onset of the project, we need the loads. We need the loads because that answers a fairly fundamental question for the open loop system. How much water do I need? Here we've got, I've plotted out the heating and cooling loads for a rather large system that we were looking at in London. You can see months go across the top, this little sort of looks like a QR code, doesn't it? Little pixelated heating and cooling node. As you might expect, we've got and we've got hours in columns for every day down the sort of in the y-axis, as it were, of that plot. And you can see we've got heating dominant in winter, and then in around June, July, August, we've got this cooling dominant blue in the middle. That is typically the sort of level of information that we like to have to start designing our open loop system. We'll plot that as a peak and total monthly load to start to get an idea of the balance of the loads. And then obviously we calculate the flows that we need based on the COP of the heat pump, what sort of temperature change we want between the abstraction and the injection wells. And that starts to inform us how much water the system would like to have. Then the second part of that question was, well, how much space do I have? How many boreholes can I have? Can I meet the load demand? Here's a fairly typical sort of urban site. We've got an office block here in the north of England where we are actually retrofitting an open loop system. The site has a good aquifer. The client here is extremely motivated to remove its boiler, and they also want to update their cooling system. So here, because this is a retrofit project, because this is what's in the UK called a grade 2 listed building, we can't do too much to the look of the building. We're having to put boreholes in the pavement. So the number of boreholes that we can have, the configuration of boreholes that we can have, the geometry of boreholes that we have is somewhat restricted, horizontally, spatially across the site, but then also vertically as well, because we have just a single aquifer beneath this site. It's a very thick aquifer. It's called the Millstone Grit. It's a minor aquifer in the UK, and this doesn't give us any opportunities we have in some places to separate the abstraction and injection vertically through different aquifers. So here we're trying to see if we can get 4 boreholes on this site, and you can see one at each corner. So obviously there can be some fairly significant restrictions. So we've got our site geometry. We know how much water we know how many boreholes we might be able to fit on that. How do we then investigate the groundwater conditions? Well, in most of the areas I work in this case, I've shown the British Geological Survey Geo Onshore Index. This is a map of London. I switched all of the boreholes and water well records on. The width of that map is about 30 kilometers. So there's a fair whack of London across there. And you can see that there are many hundreds, many thousands in a setting like London. We can look at the borehole records that are available. You're never more than a few meters from a borehole in London, and that's you may think that next time you're walking around the pavements of London, you think, where's my nearest borehole? Well, you could check if you've got the app for the Geo Index. You might go and knock on the door and ask them if you go and have a look at it if you're keen on that sort of thing. But the point being that there are some very good records out there, and these this obviously varies incredibly between locations. We may be somewhere rather rural that has just a few farm boreholes, or we may be in a city like London that's got a very long history of utilizing its aquifer for water supply, mainly, or industrial supply. So we've got a lot of boreholes, and we can zoom into our site. We can click on these boreholes and actually obtain things like this. They've got scanned records of the right hand side. There's got a fairly detailed description of the geology. These are actually from up north again, so these aren't London ones, but you can see that the driller, when they submitted the borehole log to the regulator, to the BGS, they recorded what the geology is at different depths. On the left hand side, you can see that they've also recorded some groundwater information. They've said where the groundwater was when they drilled it. They even did a pump test, so we can see that this borehole yield. Let's see, this one could be a bit old. What we're looking at here, 1,500 gallons an hour. So that's not a bad borehole if you like gallons. And this is what this historical data is part of what informs us of of what would happen if we drill a well next or near to this one. As a hydrogeologist, this is a big part of my job. As I said, we can never know what a borehole will do at a certain location, but we can take this sort of historical data and extrapolate to our site what the similarity between this borehole and our new borehole might be. A significant sort of part of this as well, this extrapolation would be as well to consider better drilling techniques. This one was drilled in I think 1920 or so. I can't see the date there. So something like in the 1920s, I think it was. So we have better drilling techniques nowadays. We have better borehole efficiencies. We have better development techniques. And also, of course, the borehole record in this case, they've pump tested this well, but that might not be the maximum yield that this borehole is achievable. It can achieve sustainably. This might just be the amount of water that they wanted. They didn't want any more water, so they never tested for more water. So we can consider this a lower limit for the water availability. And then, yeah, based on that, based on collating records in the vicinity of our site, we can begin to design our well, and we can begin to understand how much water we might get from an individual well. There's also published groundwater maps. Again, in this case, you can see London maps there. These are historical maps going back to 2008. There's the bottom graph there has got water level records going back, I think to 1985. There are published sources of this information available. Most jurisdictions have some sort of geological survey or the local licensing or regulatory groundwater group would have some historical maps. And based on this, we can begin to understand not just the geology and groundwater at a point that we get from a well, but we can start to understand the spatial distribution of groundwater, its flow direction, which is obviously very critical. As a rule of thumb, if we have a unidirectional system, or what I refer to as a pump and dump, we would normally want the abstraction well to be up hydraulic gradient and the injection well to be down hydraulic gradient, so that our thermal plume of warm or cold water moves away from our site. And then this is the sort of information we get here. These maps show much like a topography surface. It shows the top surface of groundwater. So based on that, we can see which direction it's flowing in, because of course water flows from high to low elevation, and that starts to inform us of the groundwater conditions. And as I've said earlier, there are permitting constraints and opportunities on open loop ground source heat pump systems. Again, I'm using the example of the London Basin because well, this is what I often work in. They have a permitting guideline whereby the groundwater level has to sit within an ideal geological strata. So it's not that it's a set depth below ground level. It's actually according to the strata, and as you may know, the London Basin, we've got a syncline that dips gently approximately towards the centre of London. So they try and keep the groundwater within one of the strata. They're called the Lambeth group. There's very good reasons for this. London has had rising groundwater since about the 1940s. That's because lots of industry and breweries moved out of central London. They stopped extracting groundwater. In the meantime, we built a lot of underground structures and deep basements and all these sorts of things. And as groundwater has risen, these structures have been impacted by re-wetting of the London clay, which changes its strength as it swells and contracts as it gets wet and dry. So the Environment Agency have actually tasked with trying to maintain a groundwater level. So we can't just inject water until we bring that, till we raise that water level too high, and we can't abstract below the base of the Lambeth group because that dewaters that aquifer unit, and dewatering that aquifer unit actually has implications for has hydrogeochemical implications for the water. So we have to work within the constraints of the site. And I think probably another point that's worth bringing up here is I've been talking about abstraction and injection wells. Now, there is no reason from the system point of view why we should be putting that water back in the ground. In fact, it would be a lot easier if we just took the water out of the ground and then we would dump it in a river or a drain or a sewer or something like that, because then we never have to worry about the hydraulic and thermal interference between the wells. The reason that best practice and most regulators insist we put the water back in the ground is because this makes our systems resource neutral. We have no net abstraction. We have no impact on the water resource. Obviously, anyone that works in this industry, the water resources, the protection of our water resources is an absolute key driver for any abstraction and injection, and we have to ensure that water is available for the environment. We have to ensure that water is available for other water users, public water supply. I think about 1/3 of London's drinking water comes from the same aquifer that we're dealing with here, the chalk aquifer. So we can't just be pumping this water out and disposing of it in the river. That would be considered a waste of water. And so it's a regulatory driver that means we're putting that water back in the ground. And that's obviously a huge part of our open loop projects. There are sites where we can take out of an aquifer and put into surface water, and that's considered fine. And obviously that has cost savings and so on. But yeah, this hopefully this would all become apparent during the feasibility study stage. So before we've started designing the system too far, we understand the feasibility. At the feasibility stage, what are these permitting constraints and opportunities? So once we've collected all this borehole data, once we've looked at published maps, once we've looked at the licensing opportunities and constraints, as hydrogeologists, we come up with a conceptual model of the site, which at best is the picture in the hydrogeologist's head of what the geological profile is and what are the controlling factors relevant to an open loop ground source heat pump system on that site and in the vicinity of your site. So which direction groundwater flows, what the sustainable yields might be, and we use this conceptual model to test various scenarios for the sustainable yields on the open loop system. And as I said, this is probably what I've just already said. We use the conceptual model. We have a preliminary design of the borehole, so that might include the depth and diameter, what sort of casing we might need, what sort of well screen we might need in the borehole, what the pump depth would be, because obviously, as I said earlier, we draw water down in an abstraction borehole that when we switch a pump on, the level to which that water, we have to try and predict the level to which that water will fall, and based on that we can start specifying pumps, bore diameters, bore depths. So that's on the right hand side there. That might be a fairly typical preliminary design of an open loop borehole. And then on the left, as I said, we've got the sort of spacing, orientation, layout, basically the geometry of the open loop boreholes. So we try and, as far as possible, match what the building loads are, or in this case, we've got a small domestic system for a small district system for a university campus in the UK, and you can see that it's a fairly greenfield campus, but we've got lots of space. But we don't want to put those boreholes too far away from the plant room. The plant room there is a sort of a orange color in the middle of that blue circle there, and we said, well, what can we do within about 100 meters of that plant room, central plant room, in order to help this district system work? So at the feasibility stage, we should have a fair understanding of what sort of loads we can service based on the number of boreholes we think we can get in, based on the available delta T, the available injection, the abstraction and injection temperatures, which might be in collaboration with the heat pump designer, what temperatures we can accept, or that might be according to the regulatory constraints. I should probably mention here that in the UK, generally we're not allowed to put water back in the ground at anything above 25 degrees C. So we have a restriction on the flow, we have a restriction on the delta T, and then we can start discussing with the engineers about what's a reasonable thermal load that we can sustainably supply with an open loop system. And that's when we can start talking about hybrids, including air source in there, including chillers or whatever that might be. Obviously, as there are more and more larger systems coming up, we start looking at CHP plants, retrofitting and decarbonising them. We're looking at other sorts of these sort of central plant room systems. And I would say as well, we're also seeing many more the sort of the 4th, 5th generation district energy schemes where we don't have a centralised plant room, where we have just a loop connecting all the buildings, and we have a distributed system. So heat pumps in individual heat pumps in every building, individual heat pumps in every apartment, whatever that might be. And I think we're seeing more of those. And it's this at this feasibility stage that we should have a really good idea of what those balances of plant are going to be. As I said, the contribution of an open loop borehole comes with some uncertainty. So we try and give a range of possible heating and cooling loads. Now here I've just shown it's a table with the peak heating and cooling loads. I've shown a range of possible delta T's that we might be working at. So delta T being the difference between the abstraction and the injection temperature, a range of COPs, and then I guess the most important bit is the 3 rows at the bottom is we've tried to put some probability on the likelihood of getting a certain flow rate out of the ground. At this site, we thought your best chance would be to start the design, assuming that you're going to get 20 litres a second out of 2 pairs of open loop boreholes. So by that I mean 4 boreholes in total, 2 abstraction, 2 injection. And at this site, I've decided that we can get about 20 litres a second. That would be the most likely scenario. And then that has a certain kilowatt peak loads that could supply. So it's a fairly simplistic look. It doesn't look at the annual balance. It doesn't look at the total annual flows. It's just a snapshot of the peak. And I've said that there is some chance that your 2 pairs of abstraction and injection boreholes may just do 10 litres a second, and there's some chance it may do 30 litres a second, and we can continue the design on that basis. Permitting, I think it's 1:45, right? I'll keep going. This is a typical permitting sort of route. We, as I said, we do the feasibility study in the red bubble there, in the dashed line. We have certain desktop approvals. We can undertake the drilling and testing, and then we can go through the licensing process. The drilling and testing, well, as I said, often we're on urban sites, and we can have fairly small footprints working in pavements. We might be able to get a drilling rig on a fairly small 20 by 15 or sort of 60 by 7.5 meter site in order to get all the drilling equipment in an urban setting. Obviously, we don't have to worry about this if we're on an agricultural site, perhaps where we've got fields and paddocks to put the boreholes in. The testing, obviously, we want to test the wells once we've drilled them, so we do abstraction and recharge tests. It's just an example of the sort of water level plots that we get there when we switch pumps on and off. You can see the water levels going up and down. This is often a regulatory requirement, but it's also part of our design and pump selection. So that gives us some of our environmental impact assessment and detailed design. Once we've drilled and tested the boreholes, we can move on to this. So I think I'll probably skip through this quite quickly. But as I've touched on earlier, our 2 main areas of interest are thermal and hydraulic impact. So thermal impact being what happens to the warmer water or colder water once it's gone into the ground. Does it come back to your site? Does it come back to your abstraction borehole? Does it migrate off-site and perhaps go to a wetland, which we don't want to warm up? A hydraulic impact, are you lowering or raising the groundwater levels to an unacceptable elevation? this is an example of the thermal modeling we might do for an open loop system. You can see the two flags next to each other are is a cooling dominant single pair ground source heat pump system where we have an abstraction well on the left and an injection well on the right, and then down gradient from that you can see another flag. That's someone else's abstraction well. And you can see that our modeling here demonstrates that we're beginning to get a little bit of potential thermal impact as the warmer water is drawn back to the abstraction well, but we definitely get some thermal impact at the down gradient borehole. And this is the kind of thing that we need to understand for licensing. It's the kind of thing we need to understand for our own system design. A point worth making as well is, of course, you switch the system on, but it may take many years. You can see the graph on the bottom there. We can see that this is a strongly cooling dominant system based on that annual plot that I showed earlier. The graph above that is a 35-year model run, and you can see that the heating and cooling load makes the temperatures go up and down. And it actually takes 30 years for this system operating as designed to sort of reach a dynamic equilibrium between the abstraction and the injection temperatures. So that we can't know what's going to happen the year that we turn it on. There's actually we have to look into things like the thermal models to help us design what's going to be truly sustainable in terms of abstraction rates and thermal loads on an open loop borehole. Again, this is a bird's eye view of a model I did recently in London. It's got abstraction injection wells, and you can see that those contours are the groundwater levels, obviously lower around the abstraction bores, higher around the injection bores, and the way that interacts is something that we can't guess before we switch them on. We have to model what that's going to look like in a numerical model. Again, I've touched on earlier what the thermal plume might look like. This can stretch off for, in this case, I think we've got about 150 meters away from the site. We've got this thermal plume for this cooling dominant system sending warm water down gradient. Now that's of interest to the regulator. That's also of interest to you as the designer, because we can't adversely impact anyone else as well. And you can see on that green block is an oblique view of the groundwater model with a slice cut out of it. And you can see that there are no flags, which are boreholes in the model, that are likely to be impacted by the operation of our system. I've talked about the range of target groundwater levels already, that we have to try and maintain that within a certain unit. So I guess a question often asked at the feasibility study or even at the detailed design, what's the minimum distance between your boreholes? Well, I'm afraid it's how big is your site, how much flow is required, what's the thermal imbalance, what are the groundwater flow mechanisms, which I haven't really touched on, but we have different sort of groundwater flow. What's the groundwater through flow? So what's the hydraulic gradient through your site? What's the context of your site? Are you in an area where there's ecological features or groundwater temperature sensitive abstractions? I'm afraid the answer to that is there is no simple answer. You better ask an experienced open loop designer. So following on from that, well, when do I need to ask when do I need a groundwater model? I'm afraid you better ask an experienced open loop groundwater heat pump designer. We don't always need a model, but certainly to progress, to de-risk the project and to progress in a sensible manner, I think an open loop system should be under the guidance, at least, or the oversight of an experienced designer. So just to pretty much clarify, abstraction and injection licenses tend to have monitoring requirements for the operational phase. So once we design and build it, we can't just leave it. We have to monitor that. We have to obviously incidents that we touched on earlier. And of course, groundwater changes. We've got climate change. We've got other abstractions coming into the equation. We're dealing with a natural system. Things can change. The building can change, of course. It might not be used as designed. So in order to optimize the system, we can't just hand it over to the building, the building operator, the maintenance guy. We need follow up. We need to monitor the system. We need to make sure the maintenance is carried out. And if we're really going to optimize the system, we need to consider any changes to the assumptions that we've made in our assessment. And hopefully at 10:02, that brings me to a thank you for listening.
Okay, thank you, Hugh, for your presentation. It was very interesting. We got one question from Richard through the chat, so I don't know if you can check it, or if you prefer allow Richard to speak and do on live. Maybe it's better that he can speak. So Richard, if you want to do the question for Hugh.
Hi, Hugh. Thank
Hi,
you.
Richard.
Very good.
Pleasure. Thank you.
So my question was, okay, you've got these maps and we're drawing off and we're taking London as an example. Is it likely that these temperatures are going to keep increasing and the ability to actually do our exchange is going to be reduced to not be able to use open loops?
That's an excellent question, Richard. And interesting enough, I was in Brussels last week at the International Association of Hydrogeologists annual conference, and we had quite there was a few presentations on this exactly, and we also had quite a lively debate in the bar afterwards. In the case of most jurisdictions, we have to go through this licensing process where we have to observe the potential environmental impact of our system. Now, the Environment Agency in the UK, in England, I should say, wouldn't allow us to install a system that we think would have a direct adverse impact on another system. So it's got one level of regulatory sort of scrutiny at that level, our individual system. But as you're asking, what's the cumulative impact? Now, that isn't necessarily a requirement of an individual system to show that there's no cumulative impact. You could argue that that's probably the job of the regulator. And as it stands, most jurisdictions don't require you to consider the cumulative impact directly in your own assessment. So the short answer is yes, there is the potential for a city like London, which most buildings are going to be cooling dominant, to potentially start heating up the aquifer, whether that's in a regional scale or whether that's in a local scale, in a small cluster, like let's say in the City of London, where we've got development constantly happening. They're telling me that London's never finished, so they're all going to keep building something. They will potentially be putting more and more cooling dominant systems in a small area, and we may well get pockets of higher heat that may well adversely impact the operation of the systems. Now, in the Netherlands, the regulator actually requires all open loop ground source heat pump systems to have balanced loads, and that balanced loads that you have to submit to the regulator every year what your heating and cooling loads actually were, and if you go significantly out of balance on a rolling 5-year average, they can take your license away, or they can impose some extra restrictions to ensure that you do balance. So there are different ways of imposing that, and obviously there are case studies where a thermal imbalance has led to unacceptable changes locally in groundwater temperatures. So yes, to go back to your question, yes, we have some potential. I believe the regulator has to be aware of this as a potential issue, and we cannot keep going putting warm water in the ground indefinitely. Excellent question. Thank you, Richard.
Okay, if someone else have more questions, please let me know. I can give you access to your microphone. If not, thanks so much for being with us today. Thanks again, Hugh, for your presentation. It was very, very nice. And after the training, we are going to, we need to release in a couple of days. We're going to release the video that we need to edit a little bit, and the presentations. So in a couple of weeks, we were going to do another one. You can register through our website. So thank you so much for being with us. Have a nice day to all of you. See you soon. So I'm going to close the meeting. Bye-bye to everyone. Bye, Hugh. Thanks again. So see you.
Pleasure.
My pleasure also. Bye bye.
Thank you very much.